I'm Ava Slovensky. I'm in Miss House's third block stats class, and welcome to my very first Quideo. So first up, we have our basic question. Our basic question asks us, do heavier people burn more energy? Metabolic rate, the rate at which the body consumes energy, is important in studies of weight gain, dieting, and exercise. We have data on the lean body mass and resting metabolic rate for 12 women who are subjects in a study of dieting. Lean body mass, given in kilograms, is a person's weight, leaving out all fat. Metabolic rate is measured in calories burned per 24 hours. The researchers believe that lean body mass is an important influence on metabolic rates. So, in other words, the question wants to know the relationship between a person's metabolic rate and their mass. So we can see right here, it gives us all the masses of the 12 peoples and the rates burned per 24 hours. So we go to our calculators to help calculate and construct a scatter plot. So we go to Stat, Edit, and then you can go ahead and put in all of your masses in L1 and all of the data for metabolic rates in L2. As you can see, I've gone ahead and already done this. So then we're going to go to second, y equals, and then we're going to stat plot. We're going to make sure our stat plot is turned on, as well as our x list gives us L1, and our y list is L2. And then we're going to zoom 9, and right here gives us our scatter plot. So I went ahead and wrote out our scatter plot for an easier visual for us. When we look at the scatter plot, we use the data given to decide the direction, form, and strength of the scatter plot. As you look at the relationship between the x variable, the explanatory variable, which is the lean body mass, and the y variable, the response variable, which is the basic metabolic rate. Look at the direction relationship. We can see that it is positive because when you look at the higher masses, you associate them with the higher end of the metabolic rates. We can also say this for the lower rates and the lower masses. The form determines the shape. So basically, it is if this is linear, curved, or nonlinear. We can see the scatter plot pretty much follows a straight line, aside from the one point, which is up here. This is tied to a linear form. Lastly, the strength determines how well correlated the two data sets are. This is based on how closely the data set follows the linear line. So if we were to draw a line through the data, we can see that it does in fact stay near the line, proving that there is a positive linear relationship between the variables. So I'm going to go ahead and just draw a straight line. We can go ahead and see that most of the dots are very relatively close to this line. These findings confirm that the researchers' beliefs about lean body mass directly affecting the metabolic rate are true. So next we're going to look at our advanced question. The advanced question states, the data in the accompanying table are from the paper 6-Minute Walk Test in Children and Adolescents. Boys completed a test that measures the distance that the subject can walk on a flat, hard surface in 6 minutes. For each age group shown in the table, the median distance walked by the boys in the age group is given. It provides us with the data representing the relationship between the representative age, which is the midpoint of the age group, and the median of the 6-minute walking distance. In other words, this question is asking us, how far can these children travel in 6 minutes in meters? To determine the relationship between the two variables, the explanatory variable being the age, and the response variable being the distance walked in 6 minutes, we must calculate the least squares regression line. The least squares regression line gives us the general trend to how the response variable changes as the explanatory variable increases, providing us with a linear representation of our changing data. First, we go in our calculator, and we hit Stat, and then Edit, and this gives us our list. And in L1, we can go ahead and enter our data for the representative age, like I've already done. And then you go over to L2, and you're going to go ahead and enter your median walking distance, like I've already done. Then once you've completed that, you go to Stat, and then you go over to Calc, and then 8, which brings up this. You can go all the way down to Calc, Enter, Enter, and it brings us this, which gives us our value of A, 492.7977. B, which is our slope, which gives us 14.7633. R squared, and R. So once we've gone ahead and done this, we can get our formula that follows, which is y hat equals 492.7977 plus 14.7633x. Because our projection starts at 3 rather than 0, we can't adequately say that 492.7977 will give us an accurate projection. However, we can use the slope, which is 14.7633, meaning that every time the child's age increases by 1 year, the median distance they're able to travel increases by this amount, 14.7633 meters. However, in saying this, this does only apply to the age groups 3 through 18. So, in saying this, if you were trying to predict the distance walked by someone who is not within the range of 3 to 18, the distance walked by someone in this range would be very inaccurate. Now, to create a residual plot for this data, displays how each age group relates to our least squared regression line. There is no trend between the residuals and the representative age that we see here. So right here on the y-axis, we have the distance walked in the median 6 minutes. And over here, we have the representative age along the x-axis. So there's no trend between the residuals and the representative age. And it's scattered throughout, which means it gives us a strong linear data relationship. This is normal, meaning that there are not any unusual features. If there were unusual features, we could say the relationship between the residuals and the representative age are not correlated and contain a nonlinear and most likely weak relationship. However, we can't say this because our graph is normal. So the AP question states that commercial airlines need to know the operating costs per hour of flight for each plane in their fleet. In a study of the relationship between operating costs per hour and the number of passenger seats, investigators computed the regression of operating costs per hour on the number of passenger seats. The 12 sample aircraft used in the study concluded planes as few as 216 passenger seats and planes with as many as 410 passenger seats. Operating costs per hour ranged between $3,600 and $7,800. Some computer output from a regression analysis of this data is shown below. So I've used this graph and the information that we're given to sketch this graph right here. And it shows us the predictor coefficients for the constant and the seats. The constant was 1,036, and for the seats it was 14.673. So, part A asks us for the equation of the least squares regression line that describes the relationship between operating costs per hour and the number of passenger seats in the plane. We are given the following two coefficients, 1,036 and 14.673. We'll use 1,136 as A, and B will be 14.673. The squared regression line turned out to be y hat equals 1,136 plus 14.673x. So because A is 1,136, it equals the constant for the operating cost per hour. B is 14.673, which represents the number of seats in the plane. B is also the slope. This means that it represents the number of seats that increase for every increase in the operating cost. That can be seen right here in our scatter plot. Part B asks us, what is the value of the correlation coefficient for operating costs per hour and the number of passenger seats in the plane? Interpret this correlation. So the correlation coefficient is R, which we can see right here. We are already provided with R squared, which is 57%, which is also equal to 5,700. To find R, we're going to take the 57% and square root it. When you do this, you get 0.75498. Since the R value is relatively close to 0, it indicates a weak linear relationship. The linear relationship increases as R approaches 1, moving away from 0. Since 0.5498 is closer to 0 than it is to 1, the linear relationship is weak. The points in the scatter plot lie in a relatively straight line, so if it were closer to 1, we would be able to see that the points go in a straight line. If we take a look at our scatter plot, we see that they are in fact grouped in clusters. I've outlined some of these clusters in orange, so we can see right here, there's a cluster right here and right here. Since the R value is closer to 0, it indicates a weak linear relationship and the lines are not in a straight line. The R value indicates a weak correlation because it is non-resistant. Part C asks us, suppose that you want to describe the relationship between operating costs per hour and number of passenger seats in the plane for planes only in the range of 250 to 350 seats. Does the line shown in the scatter plot still provide the best description of the relationship for data in this range? Why or why not? So what part C is asking us is if we were to decrease the range of these parts from 250 to 350, would this line still describe the data? And we can answer this question with no. The line shown in the scatter plot would not provide the best description of the relationship with the range from 250 to 350. This is because if we were to remove the 5 points from the scatter plot, the least squares regression line would not accurately describe the data we have found. The current least squares regression line is currently influenced by the potential outliers we see in this graph. We can view these points from 200 to 250 and 350 to 400 as potential outliers. This would influence the change on this line. I've outlined them right here in orange so we can clearly see them. If we were to take away the values at 250 and 350, this would not accurately describe our linear regression line.